to have Jiaqi speaking to us about building quantum engines for large-scale decision-making. Jiaqi is a postdoc at the Simons Institute for Theory of Computing and the Department of Mathematics in Berkeley. He got his PhD in 2024, and his work focuses on quantum algorithms for large-scale optimization, machine learning, and decision-making. So we're really pleased to have Jiaqi here, as I stalled for a little bit of time. Yep. And so I want to ask you to please join me in welcoming Jiaqi Leng.
Yeah. Thank you so much for the introduction, and it is really my honor to be here and give my this presentation on my work on building quantum engines for large-scale decision-making. So what is decision-making? If we open a dictionary or if we go to Wikipedia, you'll see this very standard textbook definition, which is we try to choose the optimal strategy or some actions based on the input data and criteria. Because we're in computer science, we care about computational problems. And speaking of decision-making, usually that refers to optimization, optimal control, those type of problems. So those problems are actually very central in computer science. For example, in machine learning, artificial intelligence and robotics, we have many different challenges in this category, including this complementary optimization, deep learning, for example, we want to train those neural networks, that's an optimization problem, and also this motion planning in sort of robotics. So decision-making problems, as I mentioned before, they could be very challenging, especially in those kind of large-scale high-dimensional setting. So here I listed a few common kind of computational barriers or bottlenecks for those kind of problems. Speaking of optimization problems, we usually will have this kind of non-convex optimization landscape. For those problems, we could have more than one local minima, and some of them are not globally optimal. So because of this kind of non-convexity, gradient-based algorithms usually fail to give very good results. In some of the other systems where we have different computing components, there could be computational latencies happening at some of those components in this kind of full feedback loop, and this could also slow down the computation a lot. And also, speaking of some of the data-driven approach and integration with real-world data, we could have noisy data distributions. And in terms of algorithmic runtime, this could mean a high or large sample complexity. So our observation here is that for many of those hard problems in this field, they usually requires a very long runtime. Usually those runtimes could be exponentially long in terms of the problem size. And because of this, we think those problems are kind of natural target for quantum accelerations. So speaking of quantum computers, I guess we have been looking at this kind of idea for many times, but still I want to spend a few minutes to talk about what is actually a quantum computer. So quantum computer is based on a very different set of rules, computational models based on quantum mechanics. In the classical world, we have bit, and a bit can either take the 0 state or 1 state. So if we have n such bits, they can represent at most in total 2 to the n number of combinations or possibilities. But because on class computer, we can represent a single bit string at the same time. So at each time, we can represent one of such an exponential number of combinations. However, quantum computers, they use a fundamentally different information processing unit, which is called a quantum bit or qubit. Those are two-dimensional complex vectors. They are linear combinations of the 0 state and the 1 state as like a bit. And if we have n such qubits, we'll actually have a so-called superposition, or mathematically speaking, linear combination of all those 2 to the n states. So that gives us an exponentially large vector space where n qubits can, in principle, represent a exponential size vector. So in this case, we can represent much richer information than a classical system. So quantum computation usually refers to some quantum circuits that were made by elementary quantum gates. Those gates are sort of like the building blocks or elementary operations on quantum processors. And when we talk about an efficient quantum algorithms, usually that means we want to have a quantum circuit operating on a polynomial number of qubits and also a polynomial number of gates, where here the polynomial is in terms of the n, which is the problem size or input size. That's how this computation model is defined for quantum computers. And now let's go back to decision making. So as you may heard of, many of the big players in this field, such as IBM, they have their very kind of ambitious roadmap, long-term roadmap, all the way towards 2033. And they identified 4 different areas as their kind of commercial applications, potential applications of quantum computing, including security, chemistry, optimization, and machine learning, where the last 2 challenges are basically the core computation subroutines that we have in decision making. And this is also like identified by those big companies, big players in this field. So now I think the goal is pretty clear. We want to achieve this kind of quantum computational advantage in those big class of decision-making problems. But what are the current existing paradigms in this field? Currently, we have 2 different approaches. The first approach relies on this parameterized quantum circuit, which I'll introduce in the next slide. And the second approach is the so-called quantum-enhanced classical algorithms. So for parameterized quantum circuits, the idea is that we try to use quantum circuit in a way like what we do with neural networks. So in neural networks, it's kind of like a parameterized, or some people say it's parameterized map, where we have those different weights. And we can also have parameterized gates in a quantum circuit, and this gives us sort of like a quantum neural network. This is how some people call this kind of architecture. And for algorithms using this kind of quantum neural network, people usually call those variational quantum algorithms. And they find many applications in, for example, complementary optimization, chemistry, classifiers, or even generative models. So because those quantum neural networks are the classical upgraded, quantum upgraded version of those classical neural networks, so people usually expect they have better expressive power. They can represent some more complicated functions or states that classically we couldn't. And also because they were directly written down in the circuit format, those were considered to be hardware efficient. However, on the downside, this approach usually they do not have a very kind of rigorous performance guarantee. That means for larger scale systems, so far, we do not know if this approach can scale. And also, the key issue here happens to be the trainability, because in many cases, we know there is a notorious phenomenon called barren plateaus. That means for training those quantum neural networks, the gradient information could vanish exponentially with the system size. In that case, we do not have gradient information, and it's very hard to train those quantum neural networks using gradient-based methods. Okay, and then there's a different approach, which is this quantum-enhanced classical algorithms. And the idea is also kind of straightforward. We start with a classical algorithm, and we try to identify what is the slowest step in this classical algorithm, and we try to accelerate this specific step as a kind of computational bottleneck using an existing quantum algorithm or quantum subroutine. So here I have a table. This is by no means a very complete list, but I just listed a few basic problems. For example, Monte Carlo sampling, linear system solve, or Fourier transform, where we do have very established quantum algorithms to achieve computational speedup ranging all the way from quadratic to exponential. And here, I also listed a few examples of how we can leverage those faster quantum subroutines to accelerate existing classical algorithms. And because of we do have a very rigorous analysis of those classical algorithms, this approach usually leads to provable or rigorous quantum advantage. That means we can show like the upper bound, for example, computational upper bound on how much time we need for those quantum computers to solve the problem. That means if in the future we have larger quantum computers, this could mean better scalability because we know it's going to scale because it's rigorously proven. However, on the downside, those algorithms are usually based on existing classical algorithms. For example, in this case of estimating convex body volume, we need to start from the classical algorithm and try to use quantum kind of Monte Carlo sampling techniques to improve it. What if there is a problem and we do not have a good enough classical algorithms to start with? Then this approach basically rules out the possibility to have a genuine kind of quantum algorithm design which has no kind of classical counterpart. So it's sort of limit the design space already. And also another big issue is that this type of algorithm, they usually do not have any knowledge or assume any knowledge about the lower level quantum hardware. And this usually lead to some sort of like, the kind of a separation or kind of gap between how the algorithm is designed and how the hardware is implemented or executed. So there could be a substantial quantum resource requirement. So that means this approach is not very ideal for near-term implementation. So now, as we can see, these two approaches, they focus on very two different aspects of quantum advantage. This first approach focuses on practical quantum computing, while the second approach focuses mainly on this probable quantum advantage. However, as I mentioned before, there is a kind of significant gap between these two approaches, because for many of those rigorous algorithms, we don't have hardware efficient implementation, and the other direction, many of those algorithms, they do not share or they do not benefit from probable speedups. And this is exactly the target that in my research I try to address. So instead of having this kind of two separated approach focuses on different aspects of quantum computing, I propose that maybe we should consider kind of like a unified quantum computing engine, where at this core of this engine, we have these quantum algorithms. Hopefully, we do have those probable quantum speedups. So we know this algorithm or this engine can scale no matter how large the problem size is. And we have the supporting software system that will help us to deploy these quantum algorithms on sort of existing quantum hardware. And this has to be also take the hardware specifics into consideration. So this becomes like a co-design between the algorithm and software side and also what we can actually do from the hardware side. And by having this kind of quantum computing engine, we can just take in the problem input and then give the output, just like how classical computer science solved the problem. And this approach actually has this kind of twofold advantages. First, this approach usually gives us rigorous quantum speedups because we still can leverage the problem structures in terms of how we design the quantum algorithm. And many cases, we can show there will be from polynomial to exponential quantum speedups. And on the other hand, because we also are aware of what is the kind of corresponding quantum hardware there, so we can also benefit from this hardware efficient implementation. And I'll make this idea more concrete in the two projects that I'm going to present today. So the first project is to have quantum speedups and supporting software for continuous optimization. And the second project is to have sort of polynomial speedups for linear control problems, where we also talk about how this kind of framework can lead to a more kind of efficient hybrid quantum classical design. And for both of the projects, I'm going to be talking about both the probable side and how we can make it to be more practical. Okay. So now let's start from the first project. So speaking of optimization problems, I think let's start from the very basic, very standard formulation, where we care about this kind of continuous functions in the Euclidean space. It's an unconstrained optimization problem. And the standard method, the go-to method many people think about is this gradient descent method, where we just follow the gradient descent directions with certain step size, and then in many cases, we'll just converge. So this has been a very big success for large-scale optimization, especially machine learning, because we have really large problems. And we do have good theoretical guarantees for gradient descent. However, for non-convex problems, initializations actually matter a lot. For example, here, in this kind of one-dimensional non-convex optimization landscape, we have two local minima, while only one of it is global, another one is actually local optimal. If we happen to have a good initialization, then with just a few iterations, we'll be able to find the global minima. However, this is not the case if we are not lucky enough. We had a bad initialization, and in this case, even you do a lot of iterations, you'll get trapped in those local minima without any chance to escape from it, because we only use the gradient information in this algorithm. So now let's summarize our observations here. In gradient descent, by just following those locally optimal updates, like the gradient descent steps, we could end up with globally suboptimal solutions. While if we want to get a global optimal solutions, sometimes you need to take a path that is not locally optimal. So in this case, gradient descent plus bad initialization could give us, in some cases, zero success probability if we're really not in good luck. So what quantum computer can bring like new ideas into this picture, we think about this natural idea of superposition, because this is how quantum is distinguished from classical computation. One of my favorite example to illustrate superposition is this very famous Schrodinger's cat picture. We can have a cat in two different situations. One, this is a living cat, very happy, and this is a dead cat, not very happy. And we could have an equal superposition of these two states you can just think about it to be a 0 state and a 1 state. And by measuring this quantum state, it's like you have this kind of superposition cat in a box, and you open up the box, you just want to check what's the current situation of this cat. It could be either 50% chance to be living and another 50% chance to be a dead cat. So this is great. What if we can turn this sort of superposition idea into optimization and consider something to be Schrodinger's gradient descent? The idea is that, for example, if we can have a superposition of both the path 1 and path 2, and if we do like a quantum measurement, just like how we measure the cat, you actually end up with a 50% success probability because you have 50% chance to measure this second path. Although this path is not classically viable, we still have some chance in this quantum system, and you'll end up with a 50% success probability, which is very different from what you can do in the classical gradient descent case. Okay, I think this is just like a high-level conceptual idea, and now I'm trying to make this idea kind of more rigorous. So here I have to make this quote from Richard Feynman. He said, our particles in this world, they do not just take one path. So this is a fundamental observation, not just in computational science, but also in physics. So quantum particles, they tend to explore all possible paths from one point to another one. So in this case, a quantum evolution can actually be formally formulated as an integral of all possible paths. And because of this interference of those between those paths, we actually expect that this process cannot be classically simulated, even use a massive parallel computing system. So this is some sort of intrinsic quantum dynamics. And just like in this picture illustrated, we need to consider all different paths from one point to another one. And this leads to our idea of this quantum algorithm, which is what we call this quantum Hamiltonian descent. So in this algorithm, we try to simulate this kind of integral of all paths, and this will lead to a quantum evolution process. And because we are simulating not only the classical gradient descent path, but also those unclassical paths, we have better chance, hopefully, to identify the global minimum. Okay, and now to make this idea kind of mathematically rigorous, we need to talk about math, of course. So we start from an advanced version of classical gradient descent. This is called Nestrov's accelerated gradient descent. It's a kind of gradient descent with a certain extra piece of momentum information. So by adding this kind of momentum into the standard gradient descent, we have faster convergence rate. And it has been known since 2016 that this kind of Nestrov's AGD can be actually formulated as this kind of continuous time Hamiltonian mechanics. So this mechanics is described by the Hamilton's equation, and we have this classical Hamiltonian function. This is a function of both the momentum and position, and they are time dependent, and the generated dynamics basically simulates or sort of mimics the Nestrov's AGD. By applying the path integral formulation on top of this classical Hamiltonian system, we'll end up with a quantum Hamiltonian, and this is what we call a quantum Hamiltonian descent. In this quantum case, we again end up with a quantum Hamiltonian operator. Now, in this case, it's no longer a function anymore, because in quantum mechanics, everything is like operators and states. So in this case, we have this quantum operator, this quantum Hamiltonian. It also has a time-dependent kinetic energy and a time-dependent potential energy, just like in the classical sense. However, the dynamics generated by this quantum Hamiltonian becomes this famous Schrödinger equation, where we have this wave function psi. It is a function of both time and position, and it's like a field, kind of field function in the whole space. The function itself is complex valued. However, we can think about the modular square of this function, and it gives us kind of like a probability density function in the whole space. And by performing this kind of quantum measurement, just like how in the Schrödinger's cat case, we open the box and we look at where is the quantum particle, we can also look at where is the quantum particle given this quantum state. And the quantum measurement is mathematically equivalent to draw a sample from the corresponding probability density function. And the Schrödinger equation is a linear evolutionary equation, and this can be easily simulated using a quantum computer. And now, by applying this idea to optimization problems, we are actually having a new kind of paradigm of quantum version of gradient descent, where this kind of quantum evolution will help us to sort of explore the whole space. Okay, and now I've been talking about a lot of high-level ideas. I think it's time for us to see some evidence. So here I show you like a two-dimensional non-convex optimization problem. This is called Levis function, and we try to run a classical gradient descent or accelerated gradient descent algorithms on it. We start from the initial distribution is from this two-dimensional uniform random distribution, and as you can see, after some iterations, all those updates collapses to those little dots, where each of these dots represent a local minimum. In that case, you see almost all like 100% chance we'll end up with something that is not globally optimal because there is a single global optimal here. So gradient methods actually cannot solve this problem very efficiently. And here, this is the quantum solution using numerical simulation, where each dot here represents a sample drawn from the quantum wave function. So that's like how we can classically say what's the current state of this quantum evolution. And as you can see, eventually those dots converges to the single point, almost like a single point. That's where we have this global minimum. And here, I guess more intuitively, we illustrate the quantum density kind of function. That's like the modular square of the quantum wave function. They are probability distributions. And as you can see, it originally started from this kind of very flat, spreading out distribution, all the way converge to something like a direct delta type of distribution, where everything converges to the global minimum. So this numerical simulation really gave us some sort of confidence that this quantum dynamics could really help, especially for hard optimization problems. And now I think we're ready to move on to the next question, which is what kind of rigorous theory we can develop on top of this kind of interesting observation. Yes, please.
Go back to the previous slide. You had this Hamiltonian.
Yeah.
How do you get that Hamiltonian on any like general purpose quantum computer?
I guess you're asking how we can simulate this quantum Hamiltonian, right? The way we can do it is we have a quantum algorithm called trotterization. It's like how we can simulate quantum dynamics. This part, it's actually diagonal in the Fourier basis. So you can simulate this part using quantum Fourier transform. This part, it's diagonal in the computational basis. And we allow, or at least we assume that like the quantum computer has access to those function values. So you can split these two terms separately using different circuits, and you can just implement their separate evolution. This will give you the full quantum simulation. Yep. Any more questions about how this algorithm looks like or the performance of this algorithm?
Trotterization, what would happen? You come back to variational algorithms for the trotterization?
Oh, so in our case, because we already chosen, there's a time schedule there. The time schedule is the same as what we have in the classical Nesterov's HD case, where in that case, we have a classical Hamiltonian with certain time-dependent functions. That's what we call the time schedule. So in our case, when doing the trotterization, we do not choose the step size in a variational way. We directly put in like the step size using the existing like time schedule function. So there's no variational training component in this algorithm. Does that answer your question? Yeah, okay. Okay, good. I think we're now ready to see some proofs, theorems. So as I mentioned before, this quantum algorithm is implemented as a kind of real space quantum simulation problem. And for those of you who are familiar with physics, we usually call this like a first quantization basis or simulation. And here, this lambda of t is what I just mentioned before, this time schedule function, where in the Nesterov's case, we choose lambda of t to be t to the cube. So in this case, as a quantum algorithm, this is actually a zeroth order algorithm, because to simulate this quantum Hamiltonian, we only requires the information of function values. We do not require gradient, although this algorithm is inspired by gradient, classical gradient methods. So this is actually a classical zeroth order method. No gradient is involved in terms of implementing this algorithm. However, we are able to prove that we can match the classical first order convergence rate. For general convex problems, we can choose the standard t to the cube schedule function, and we have this t to the -2 kind of convergence rate in terms of expectation, where those x of t are just the samples you draw from the quantum state at different time. And for strongly convex problems, we can even have a more aggressive choice of the schedule function. In this case, you'll get an exponential convergence rate. These two convergence rate matches what the classical gradient algorithm could do. However, we're just a zeroth order quantum algorithm. So you see there is actually kind of interesting separations between quantum and classical in terms of what kind of order of information we require from the functions. And also another thing I want to emphasize here is that these two proofs, these two results were established without any assumptions on the initial state. So this is conceptually and practically very different from an adiabatic quantum algorithm or what people call quantum annealing, because in that algorithms, you have to start from the ground state of the initial Hamiltonian. While in this case, we develop a different type of analysis based on Lyapunov functions, and we can show the convergence from any bounded energy initial state. Yeah.
Why the initial conditioning adiabatic is the issue? Because we start from the easy to solve Hamiltonian. We know it's grounded state. Why it's issue starting from grounded state?
Yeah, that's a good question. I'm not saying this is an issue. I think this is a feature. Because we do not have this feature, so we are not adiabatic algorithm. I guess that's the point I want to make. And the second thing is that in adiabatic algorithm, because you always have to follow this adiabatic path to make the state stay in the ground energy subspace, the so-called instantaneous ground energy subspace. But in our case, because we do not care about ground energy, that means potentially we can drive the evolution much faster, going beyond what the standard adiabatic evolution could do. I would say this is sort of the advantage. However, the difference is more like the difference in terms of how we define those algorithms. Yeah.
Have you insight about how much faster? Because in adiabatic, the time required for adiabatic process grows exponentially with the distance between grounded state and first excited states. And if we decrease that space linearly, the required evolution time will grow exponentially. And you say this approach is faster. Do you have any insight?
Yeah.
Exponentially faster? Faster, how much faster?
Yeah, later on the next slide, I'll show you more kind of like a more relevant results along that line. Yeah, yep. And any questions on this slide so far? Yep.
Maybe I don't understand this, but in a convex function, convex optimization problem, you have like convergence to global minima typically without worrying about the initial states, right?
Yeah.
Why is that so surprising?
I would say this is surprising from quantum algorithm point of view, because before this algorithm, like I guess there's no like a generic quantum algorithm that can deal with continuous optimization in this way. So I would say this is sort of like a new paradigm. Even though this analysis is for convex optimization, it's probably not practically that interesting. I would say this is like a kind of paradigm thing. Yeah.
Do you consider convex optimization non-trivial?
This problem, because convex optimization is a big umbrella, right? We have this kind of very standard unconstrained problem. We can also have constrained convex optimization problem. I wouldn't call every single problem under that umbrella to be trivial or non-trivial. I mean, some of them are actually kind of non-trivial. But the point is that for quantum computers to demonstrate, for example, exponential quantum advantage, I think quantum convex optimization might not be the very ideal case, because we already have polynomial time classical algorithms. But as I will mention in the next slide, I'll introduce two different classes of non-convex optimization problems where we do have either empirical or even theoretical evidence to show there could be exponential speedups, specifically for non-convex problems. So here I want to discuss two different classes of problems, where each of these class of problems, they are featured by some special design of the objective function with an exponential number of local minima. So because of this exponential local minima, they are very difficult for classical algorithms, especially gradient-based algorithms. And in the first case, we show we construct like a kind of class of natural polynomial optimization problems. And because of they have exponential number of local minima, we tested a lot of different classical algorithms on those problems, including those deterministic gradient-based or stochastic optimization algorithms such as perturber gradient descent or even stochastic gradient descent. We also tried some global search type of optimization algorithms based on, for example, branch and bound. And it turned out that all the tested algorithms, I think there are in total 12 or 13 of them, those algorithms, all of them exhibit exponential runtime in terms of the number of dimensions of the problem. So they have exponential runtime. On the quantum side, we were able to show that our quantum algorithm, this QHD algorithm, requires a polynomial runtime to find a global minima. And this is a kind of provable result. So this is, I would interpret this as kind of empirical separation or performance separation between quantum and classical. Yeah. We did. Yeah, it's included in one of the tested cases. Yeah. And more recently, we were able to make this kind of result even more stronger by having some kind of more kind of heavy constructions. So for the new class of problems, they're kind of slightly more contrived. Still, they have an exponential number of local minima. And in this case, because of our specific construction, we were able to prove that for any classical algorithms that requires function values to solve the problem, by solving the problem, I mean to find a global minimum, they would necessarily require a super polynomial number of queries to solve the problem. So here's like a query lower bound for classical algorithms. And on the quantum side, we will still be able to prove that our quantum algorithm can solve this problem within polynomial time. And this gives us actually kind of a super polynomial quantum classical separations in a query complexity sense between, in continuous optimization problems. Yep. Any questions so far? Yes.
For your quantum algorithm, are they also based on Oracle or it utilize some more details?
In this current formulation, we only require oracular access to the function values f.
Is it correct?
Yeah. So that's the way why we claim this is a kind of query complexity result. Yeah. But in the first case, because we know what are those polynomials, if you want to implement those polynomial optimization problems, we don't need oracles. Yeah, and we also let the classical solvers or optimizers to know the polynomial, although they cannot find a solution to the problem. Yeah.
I mean, I'm kind of curious why this doesn't mean you separated like QP, the complexity class, from NP.
That's a good question. I think this is a kind of, we call this like a query model. But for this NP, and usually you need to go down to the circuit model or the plan model. And even though this kind of super polynomial query separation doesn't imply any separation between those plan model computational classes. Yeah. But this is already kind of strong evidence. Yeah. Okay, we don't have any more questions. We can continue. So yeah, I've been talking a lot about what kind of computational speedups theoretically or empirically we can have using this quantum Hamiltonian descent algorithms, especially for non-convex problems with structures. However, we're also interested in how we can implement or deploy those algorithms to solve real-world problems like those in those different areas. So here in the middle, we need some sort of toolchain to implement those quantum optimization algorithms. And this is actually a following work, which is a software work. We developed a software library called QHDOPT. So this library is basically it's QHD-based optimizer. And we specifically require the software library to solve nonlinear optimization problems with box constraint. And the goal here is that we try to lower the barriers to use this software. So from a user point of view, you just need to input your problem data. For example, you have nonlinear problems, those polynomials, or those matrices describing those nonlinear functions. And then our software will just take in the input format. And then we have this kind of stack in our algorithm where we compile those problems to kind of the format or kind of the Hamiltonian that can be implemented on the real quantum hardware through spatial discretization and also a non-trivial embedding procedure, which I'll actually introduce later. And then we take care of the rest of the kind of post-processing of all the data, and we directly return the output to users. So from the user point of view, you just input some problems and get solutions. Very simple. And our algorithm will just take care of all the intermediate steps. Yeah. And here, this kind of mapping algorithm is called Hamiltonian embedding, as I'll introduce in the next slide. And we are currently exploring the kind of domain-specific applications with many different institutions now in this country. And using our software, we were able to benchmark the performance of our algorithm using current quantum hardware. So here, I give you this kind of table or figure. It shows the time to solution, which is a kind of metric we use to kind of evaluate the performance. The time to solution basically is the time, runtime or wall clock time required to find the global solution. And we compared both our quantum algorithm and our software with the classical SciPy-based optimizer called TNC. And as you can see, for all of these kind of 10, those were randomly generated problem instances. We didn't do any cherry picking or anything like that. We just randomly generated some of them. And then we run our softwares and classical Python optimizers on those. And we find that for all the cases, our time to solution tends to be better. And for some of the cases, we're even like 1 order of magnitude faster than those existing classical optimizers. And we implement our quantum algorithms using the D-wave quantum computers because so far they have the largest amount of physical qubits. Yep. Any questions for this kind of performance results? Oh, sorry, what?
D-wave results, please.
Yeah, so this result is already reflected the D-wave results because we deploy we use our software to sort of deploy the algorithm on D-wave. We collect the data from D-wave and then we do post-processing. So D-wave is actually part of this workflow.
Okay, so instead of using a gate-based system, you use annealers instead.
We use analog simulators. I wouldn't call those annealers anymore because we have this non-trivial Hamiltonian embedding techniques there. But we were able to deploy this kind of workflow on gate-based quantum computers. We tried IonQ by having those characterization simulation. Those problem sizes are smaller because IonQ, they are much smaller than D-wave, but we also see like similar patterns. We also see better or faster time to solution. Yeah.
Do you have some state about how many qubits you need versus your problem there?
Yeah, for those problems, those were like actually up to 10 dimensions. So for those problems, we use a few hundreds of qubits. The largest problem we tried, I didn't include it here. The largest problem we tried is a 75-dimensional non-convex quadratic programming. That means we have 75 continuous variables. For that problem, we use more than 5,000 qubits, physical qubits. Yeah, because there's still an extra layer of overhead. We need to map those logical qubits after this embedding to those physical qubits because they don't have all-to-all connections. So there is another kind of layer of overhead there. So in total, we use almost all the qubits for the largest problem we tried.
Oh.
The scaling is like linear in the problem size. Yeah.
I think we can get a Jiaqi.
Oh, yeah. Okay. Cool. Yeah. Yeah, and I just want to quickly mention this kind of Hamiltonian embedding idea, where we start with this quantum Hamiltonian descent, and this is our target Hamiltonian. Those are kind of smaller sparse matrices, while at the same time we want to implement them using QPU, either gate-based or analog simulators, and those were usually like machine Hamiltonians. They involve 1 and 2 qubit Pauli operators, and our technique is trying to find a smaller subspace in the machine Hamiltonian. So in that smaller subspace, the whole problem looks almost exactly like the problem we want to solve as the target Hamiltonian. So in this case, we achieve to simulate those sparse Hamiltonian using spin operators. And here are some mathematical ideas. So basically, we can show that the larger machine Hamiltonian is almost like a block diagonal matrix. So by evolving this matrix, we can simulate this target Hamiltonian on this upper left block. And this idea has been recently highlighted by the AWS tech blog. And we're also recently trying to explore its potential in simulating high-dimensional partial differential equations, especially those in fluid dynamics. Okay. And then this algorithm, this quantum Hamiltonian descent algorithm really inspires some of the recent work in this field, including those works by the JP Morgan Chase quantum research team. They were able to identify more kind of quantum speedups. And also on the application side, we also are looking to some of the applications in, for example, power systems and design automation. Okay. And now I think we are ready to talk about this kind of static workflow for optimization problems, where we just put the quantum problem input into this quantum computing engine, and then we take care of it. We just output the solution. But for many decision-making processes, they could be intrinsically dynamic or sequential. So in this case, for example, in robotics or reinforcement learning, we can have like a lot of interactions between an algorithmic agent and the environment. So in this case, we have to allow the quantum computing engine to also interact with a classical system. And in this case, we want to ask also the same question: what kind of provable speedups do we expect? and what kind of hardware efficiency that we might get from this kind of design. So now this here comes to the second project, which is how we can get this both of the advantages for this linear quadratic control problems. For those of you who may not heard about this linear quadratic regulator or control problems, I give like a motivating example. This is like a kind of control of the drum swarm, where we have a swarm of drums, and we want them to follow specific trajectories. In the operating regime, the drum dynamics are almost like linear dynamics described by linear equations. However, to minimize the tracking errors of the trajectories, we need to formulate some quadratic penalty functions or cost functions. So the math model becomes this linear quadratic regulator control problem, where here I list the mathematical model of it. It's a little bit complicated, but as you can see here, the objective is a kind of quadratic function in both the state vector and the control input. And the state vector and the control input, they were coupled together through this kind of linear dynamics. So this is sort of one of the most fundamental models in optimal control theory. And for the optimal control policy for this problem, it's actually a linear feedback gain matrix or linear feedback law. It says that for the optimal control input, it has to be a linear function of the current state vector x of t. So here, for example, in this drum swarm dynamics, let me try to interpret how this kind of linear feedback control works. For the current observation of these drum trajectories, for example, position, velocity, etc., this linear feedback matrix will tell us what is the current best optimal control input, and then we give this input to the drums, and they will just follow the trajectories, basically. To compute this optimal policy, the traditional or conventional method boils down to solving this algebraic Riccati equation, or ARE. This is sort of kind of complicated equation, but the main takeaway here is that this is a quadratic equation in terms of this P star matrix. And once we know this P star matrix, we can do some computation matrix modification to determine the optimal control policy K star. So classical algorithms for this kind of algebraic Riccati equations, we have different categories. For example, the Shor's algorithm or some Newton's method. Those algorithms, they usually have a runtime which scales like n to the cubed. This is because those algorithms would require a lot of dense matrix multiplications or operations in the middle, even though we start with sparse matrices. And usually without further assumptions, we cannot bring down those complexities from n to the cube to something lower. However, if we look at the optimal control policy, which is ultimately the solution of this problem, the size of this control policy is actually m times n. And this is much smaller than n to the cube. So that means, at least in principle, there could be a faster way that can bring down the overall runtime of certain algorithms from n to the cube to something closer to m times n. And we asked if quantum computers is a good kind of target to improve this algorithm, and it turned out no, because quantum is not very good at solving nonlinear equations. Even for intermediate scale nonlinear equations, we usually do not have very efficient quantum algorithms. So this forces us to think in a different approach, like how quantum computer could help. And here I want to introduce a very different approach through the policy gradient. So policy gradient is a very powerful algorithm in RL. And it basically describes like an agent which follows certain numerically parameterized policy. And by interacting with the kind of environment, the agent will update the parameterized policy and eventually converge to sort of the optimal strategy. In the LQR problem, the control policy is actually this linear feedback gain matrix. We can just parameterize the whole dynamics using this K matrix, and then we put it back into the linear dynamics, and then put the linear dynamics into the cost function. This will create a standalone optimization problem, where now the optimal control policy becomes the global minima of this new objective function f of k. So from this point, we see it's getting more similar to a standard optimization problem. And the good thing is that this optimization landscape f of k for LQR is really nice. Gradient descent can probably solve this problem. Although it's strictly speaking a non-convex function, we can still prove like gradient descent will converge to the optimal control policy. But and we just follow these gradient descent steps, where in each step we need to evaluate the gradient of this function f of k. However, the major computational bottleneck comes to the gradient estimation. Because in this case, we need to evaluate the gradient of this complicated function. And this would require solving this so-called linear Lyapunov equation. This is a different matrix equation. Now it's a linear equation. But still, because we need those kind of involved matrix, linear algebra operations in there, overall it scales like also n to the cube kind of runtime. So the overall complexity doesn't really improve in terms of the size of the problem. However, we made the observation that for this policy gradient approach, there are actually two major components. There is a large-scale linear problem, which is to solve this Lyapunov equation in gradient estimation. And then for the outer loop, which is to do gradient descent, it's actually a smaller and easier problem, even though this is a nonlinear problem. So we try to divide the work between quantum and classical, and we have this kind of quantum classical hybrid framework to attack this problem. Again, starting from this optimization landscape, for each gradient estimation steps, we introduce a quantum module or like a quantum subroutine to help us better evaluate the gradient. And then we keep another classical processors next to this quantum module, which runs policy gradient using this gradient estimation. And through this kind of iterations, we'll be able to probably find the optimal solutions, the K star. And here, for these quantum modules, basically it's kind of like a quantum algorithm to solve this linear Lyapunov equation. And we can actually say that we'll achieve exponential speedup. So this whole design gives us first like a new kind of algorithmic design, which we completely bypass the quantum nonlinear equation solver. But still, because of this division of labor between quantum and classical, this also improves the hardware efficiency by letting the quantum computers to focus on the problem that it's really good at. So here is the kind of key component in this framework where we develop these quantum algorithms to solve this Lyapunov equation, and our runtime is polylogarithmic in problem dimension. So this achieves actually an exponential speedup for solving Lyapunov equations. And the idea is based on this kind of integral representation of the solution where we introduce quantum linear algebra techniques, in particular this linear combination of unitaries techniques to do this numerical integration. And then we can represent the solutions in the so-called block-encoded matrix. And this, to our knowledge, is like the first regular speedup for a linear matrix equation in this whole field. And now we are ready to wrap up and goes to this kind of end-to-end convergence result. The input of this problem are those problem matrices. And then we want to output some sort of approximate control policies that are epsilon close to the optimal control policy K star. And here in this table, I list a comparison between our algorithms, where we call this differentiable LQR, which is basically this hybrid quantum classical workflow, compared to the classical algorithms to solve the LQR problem. And as you can see here, we actually achieve kind of like a linear and scaling in terms of the state vector size. And we have like this also like a non-trivial polynomial dependence in terms of the precision parameter epsilon. So again, I want to reiterate that classical method, they would require n to the cube runtime, even for sparse matrices. So this is like a fair comparison because in the quantum case, in some input models, we do need to assume sparsity, but even for classical algorithms that assume sparsity, they will not be improved in general words. And our overall complexity is like our kind of quantum gradient estimation times the number of iterations. And this can be all made rigorous, and this gives us the overall results here as I listed in the table. And in the parameter regime, where we have a large-scale control problems, the size of the control, the state vector is larger than the control input, and we have constant precision. This will give us actually an end-to-end super-quadratic speedup in terms of the state vector size. Again, I have to say that LQR might not be, like a very interesting or unsolved problem in this field. It's more like a theoretical model, but here, even within this kind of white box situation or fashion, we were able to show that quantum algorithms can achieve non-trivial super-quadratic speedup. And beyond these LQR problems, recently some researchers at Google Quantum AI, they were able to generalize our result to solve more general matrix equations and still achieve exponential quantum speedups. And also some people in Europe, they were extending our framework to linear quadratic Gaussian control. And also Pennyline, they have a blog post and trying to also popularize this idea of kind of differentiable programming using this kind of hybrid quantum classical system, where this is actually a major reference is actually our earlier paper in 2022, which is almost like a precursor of the result that I just mentioned. Okay. And now I think to summarize, besides this kind of traditional approach 1 and 2, I propose this kind of quantum computing engine approach where we sort of have this combined benefit between these probable quantum speedups and also hardware efficient implementations. And beyond these two projects that I just talked about, optimization and control, I also have a few other projects fall into this category of probable and practical quantum advantages. Although due to the time limitations, I won't be able to go through all of them today. And I think I still have a few minutes. I want to quickly talk about the future kind of research agenda. So towards this kind of efficient, practical, and accessible quantum optimization, I think we need to make sure that we both have rigorous performance speedup, hardware integration, and also domain-specific application. So for kind of theoretical improvement or theoretical speedups in this kind of decision-making problems, I think multi-objective optimization, or in some words, game theory, could be another avenue where we could expect, even larger quantum speedups. So those problems are natural generalization of optimization problems, either discrete or continuous, and they have deep connections with especially constraint optimization problems. And because those problems are very hard, like in general, PPAD, hard or complete. So those problems are also a kind of natural area where we could expect super polynomial quantum speedups. And also, as I mentioned, I do care about how we can implement those algorithms in a more kind of hardware efficient way. So recently, people are really excited about the error correction code idea, either in academia or industry. And it has been a kind of major topic and active field to explore how we can have this kind of more coherent organic integration between quantum algorithms and error correction code, especially, for example, for optimization or machine learning type of problems. On the other hand, we can also think beyond this gate model, where we could have this analog quantum computing or even hybrid continuous variable, discrete variable kind of architecture for quantum computation. And they could be specific purpose, and we can also design some certain algorithms by leveraging their different kind of features or architectures to get better quantum advantage in the field. And finally, I want to emphasize that domain-specific applications will be eventually the target for many of these quantum methodologies we developed. Besides this quantum software for optimization, we are also currently working on this quantum-inspired algorithm for a certain type of constraint and complementary optimization problems. And in this framework, we actually dequantize the quantum algorithm in a certain way, so it can be naturally fit into GPU acceleration. And we're currently also trying to explore applications in manufacturing, supply chain, or even healthcare systems. So I think in the future, I can just collaborate with many domain specific or domain experts and try to explore the use cases of quantum-inspired algorithms. And finally, there is a quick kind of highlight, which is I do have active collaborations and involvement in this kind of NIH Quantum Challenge. They try to identify kind of quantum use cases in healthcare, including drug discovery and genomic data analysis. We proposed two proposals, and we submitted them to NIH, and both of them were selected as stage 1 winners. One proposal focuses on this cancer treatment problems, and another one is for the city image reconstruction. In both of them, we try to explore the potential of quantum and quantum-inspired algorithms, especially those optimization algorithms and how they can be used to accelerate computing in healthcare. All right, I think that's all my talk. Thank you so much for attending.
Wait, time for a few more questions.
Yeah, sure. Yeah.
I'll stay then.
Yeah, any questions on Zoom? Okay. Yeah, sure.
Future directions.
Yeah.
Got it.
in economics type of problems where you have constraints.
Yes.
I'm curious, usually when you do that, this type of structure is not readily admit like arbitrary constraints.
Yeah.
Just like a per constraint relaxation or something you have in mind, or how is that, what's your future roadmap?
Yeah. Thanks for the question. That's a very actually good question and deep question here. I think even for classical optimization algorithms, usually the approach is that we try to turn a constraint problem into one or a sequence of unconstrained problems. For example, this interpoint methods or even this Lagrangian multiplier ideas. So still, I think for quantum algorithms, we probably want to reformulate those problems into one or a sequence of unconstrained problems, and then we explore how quantum computers can, accelerate them. But that being said, quantum state, because they are probability densities or probability distributions. So in some sense, we can also leverage this kind of very specific quantum features to represent probability distributions. This is sort of like a natural constraint that we have in the quantum world. And for many of these game theoretical problems where you want to minimize certain things in the probabilistic simplex, in that case, we naturally just want solutions to be represented as a probability, and quantum state already does work. Yeah. So yeah, there are certain constraints we can do more natively, but mostly I think we have to convert those problems to more unconstrained type of problems. Yeah.
I'm curious how you deal with ill conditioning, and if there's any ill conditioning incurred in the quantum formulation that is not present in a classical formulation.
Yeah, that's a good question. We haven't been looked too deep into yield conditioning, at least in the current scope. But I wouldn't say my general feeling is that for some of the problems, they may not be yield conditioned in the quantum case, even though they were yield conditioned in the classical case. So I think we have to deal with this kind of problems in a case by case kind of manner. We need to look at the specific structures to be able to determine if we actually suffer from yield conditioning on the quantum side. Yeah. Oh yeah.
Guessing the size of the problem and the approach with your quantum descent, particularly with that Hamiltonian embedding method. I'm curious if you could identify maybe some of the central hardware challenges that constrain the size of problems involved with those at the moment. If you maybe have ideas of how you could skirt around those or have some type of alternate optimization to increase that volume in the near.
Yeah. That's a good question. I think there could be many different aspects where I would identify them to be the hardware limitations. But here I want to mention two specific points. The first is about the physical connectivity, because many of those Hamiltonians, even if we do the Hamiltonian embedding, they would require some sort of non-local interactions between qubits. And currently, for the D-wave and also for those superconducting-based circuits or qubits, they have very geometrically local connections. And that's why I mentioned when addressing Shin's question, there will be a kind of overhead, an extra layer of overhead when we map those logical qubits to physical qubits. That's one thing. And the different thing is that I think, even for classical optimization machine learning, distributed computing is actually a major thing because the problem sets could grow very fast while we cannot make hardware that big. So to think about what kind of distributed quantum algorithm that we can have by having quantum communications and quantum networks could be another different, very interesting, but still yet underexplored area. Yeah.
I think in the time, maybe we'll take any other questions offline and please bring them down here. In the meantime, let's thank Jiaqi one more time.
Thank you.